The ground feels permanent. It feels like the one thing in the universe that simply does not move. You stand on it, build on it, bury your dead in it. Every civilization in human history has called it stable, immovable, fixed. It is none of those things. Right now, as you read this, the tectonic plate beneath your feet is moving. Not metaphorically, not slowly enough to ignore. It is grinding, compressing, stretching, and fracturing along boundaries that stretch for thousands of kilometers through the crust of this planet. And in two specific locations on Earth, locations that geologists have studied for decades, something has changed. Something shifted. And the people whose entire careers are built around understanding that movement are not using calm language to describe what they observed. That word, panic, is not chosen lightly here. Scientists are trained to suppress alarm. They are trained to hedge, to qualify, to say further study is needed. When they abandon that language, when the papers start using phrases like unexpected slip, accelerated displacement, and seismic coupling that defies our models, you pay attention. Not because the world is ending, because reality is doing something that our best models did not predict, and that gap between prediction and observation is where science either breaks or evolves. Two of the most geologically significant fault systems on Earth have moved. Not in a routine microseismic tremor buried in the noise floor of a seismograph. Not in the kind of slow, aseismic creep that accumulates over years. These were measurable, abrupt, anomalous movements, the kind that get flagged in monitoring networks, that trigger urgent communications between seismological institutes, that land on the desks of government geological surveys with the header, "Priority review required." To understand why this matters, why two faults moving is genuinely extraordinary, you need to understand what a fault actually is, not the textbook definition, the real one. The crust of the Earth is not a single shell. It is fractured into roughly 15 major tectonic plates and dozens of minor ones, all floating on a layer called the asthenosphere, a region of the upper mantle where rock, under extreme pressure and heat, behaves more like an extremely viscous fluid than a rigid solid. These plates move. They have always moved. The Atlantic Ocean is currently widening at roughly the same rate your fingernails grow, about 2.5 centimeters per year. The Indian subcontinent is still colliding with Asia, a collision that began approximately 50 million years ago and is still actively building the Himalayas upward at a rate of about 5 millimeters per year. The boundaries where these plates meet are not smooth. They are ragged, complex, and riddled with fractures. A fault is one of those fractures, a plane of weakness in the rock where two bodies of crust have moved, are moving, or will move relative to each other. Some faults are so deep they penetrate the entire lithosphere, which can extend to depths of over 100 kilometers. Others are shallow, threading through the uppermost few kilometers of crust. All of them accumulate stress, and all of them eventually release it. That release is what we call an earthquake. Here is a fact that most people do not internalize. The energy released in a major earthquake is not comparable to any weapon humanity has ever built. The 2004 Indian Ocean earthquake, magnitude 9.1, released the energy equivalent of approximately 23,000 Hiroshima-scale nuclear bombs. Not in radiation, in pure mechanical energy transmitted through 500 kilometers of ocean floor. The seafloor along a rupture zone of roughly 1,300 kilometers length was displaced laterally by as much as 15 meters in a matter of seconds. Entire sections of the ocean floor lurched, and from that lurching, the tsunami that killed 227,000 people was born. Two faults just moved. The first is located along one of the most seismically complex zones in the northern hemisphere. The second sits at a boundary that has been identified for decades as critically loaded, meaning in the language of stress accumulation models, that the fault has stored more elastic energy than the surrounding rock can hold indefinitely. Both movements were logged by global seismograph networks, including the Global Seismographic Network, which operates over 150 monitoring stations across every continent, including Antarctica, providing continuous real-time data on ground motion anywhere on Earth with a sensitivity capable of detecting events with magnitudes well below 1.0. The readings were not ambiguous. What makes a geological event cross from expected background activity into anomalous is a specific combination of factors that seismologists track with obsessive precision. The first is timing. A fault that has shown no significant surface rupture for 300 years and then produces a measurable displacement event is not behaving within its historical pattern. And historical patterns are the foundation of every probabilistic hazard model currently used by earthquake early warning systems. The second factor is style of faulting. Strike-slip faults move horizontally, with crustal blocks sliding past one another. Thrust faults move vertically, with one block riding up over another, the mechanism most associated with megathrust earthquakes. When a fault that has historically shown one style begins showing anomalous motion in the other direction, or shows components of both simultaneously, it signals a change in the local stress field that the models must account for. The third factor, the one that is generating the most concern in published literature right now, is coupling behavior. Coupling, in seismological terms, describes how locked a fault is between major rupture events. A fully coupled fault is completely locked. Stress accumulates purely as elastic strain in the surrounding rock, and none of it is released through gradual creep. When it eventually ruptures, it releases everything at once. A partially coupled fault bleeds stress slowly through aseismic creep, which reduces the energy available for a catastrophic rupture, but can also produce complex patterns of smaller earthquakes that are harder to model. The two fault systems in question had been assigned specific coupling coefficients based on decades of GPS-based ground deformation data, satellite interferometry, and seafloor geodetic monitoring. Those coefficients are now inconsistent with the observed motion. The models were wrong, not wildly wrong. Not wrong in a way that invalidates everything we know about plate tectonics, but wrong in the specific targeted way that means a parameter fundamental to hazard estimation has changed, and changed in a direction that increases, not decreases, the calculated probability of a major rupture in the coming years or decades. There is a myth worth addressing directly here, because it shapes how the public hears news like this. The myth is that earthquakes are random, that they strike without warning, without cause, without any pattern that science can decode. This perception is understandable. Major earthquakes have killed people in their sleep with no immediately obvious precursor signal. But randomness and unpredictability are not the same thing. The science of seismology has produced increasingly precise probabilistic models of where and how large ruptures will occur. The location of the next great California earthquake, for instance, is not a mystery. It will occur on one of the mapped fault systems that accommodate the relative motion between the Pacific Plate and the North American Plate. The uncertainty is not where. The uncertainty is when. And that distinction is critical because it means every new data point, every anomalous slip, every recalculated coupling coefficient, every unexpected seismicity cluster genuinely updates the estimate. What was just updated for two of the most consequential fault systems on the planet is the estimate. Geologists studying these systems are not panicking because science has failed. They are operating with urgency because science is working exactly as it should, detecting a change in the real world and demanding that the models catch up. That process of catching up is not clean or fast. It involves reprocessing years of archived GPS and INSAR, interferometric synthetic aperture radar, data to determine precisely when the anomalous motion began. It involves re-examining historical seismicity catalogs to identify whether smaller precursory events were present and previously misclassified. It involves convening rapid response working groups across national geological surveys to share data and coordinate interpretations before the findings are published in peer-reviewed journals. That work is happening now. The two fault systems at the center of this investigation sit on opposite sides of a tectonic boundary that has shaped human civilization and ended it in places more than once. The geological history embedded in the rocks along these faults contains evidence of ruptures that, by modern engineering standards, would be civilization-altering events. Turbidite sequences on the ocean floor, layers of sediment disturbed and redeposited by underwater landslides triggered by major earthquakes, record the timing of past megathrust events going back 10,000 years. Paleoseismic trenching on land, where geologists literally excavate fault zones to read the stratigraphy like a timeline, has dated previous ruptures using radiocarbon analysis of organic material buried in displaced soil layers. The record is clear. These faults do not rest forever. And right now, for the first time in the observational record of modern seismology, both of them have moved in a way that nobody predicted. There is a number that appears in nearly every serious seismological assessment of the two fault systems at the center of this investigation: 300. It surfaces in peer-reviewed literature, in USGS hazard reports, in the paleoseismic trench data from field campaigns that span multiple decades. 300 years is approximately the recurrence interval, the average time between major rupture events, for both the Cascadia subduction zone off the Pacific Northwest coast of North America and the Nankai Trough running parallel to the Japanese archipelago. The last full margin rupture of the Cascadia subduction zone occurred on January 26th in the year 1700. That date is not estimated. It is not approximate. It is known with extraordinary precision because of a piece of evidence from the other side of the Pacific Ocean. A tsunami arrived on the coast of Japan with no corresponding local earthquake to explain it. Japanese historical records, meticulous, continuous, maintained across centuries, documented the orphan tsunami. Working backward from the travel time of the wave across the Pacific, seismologists and historians collaborated in the 1990s to pin the Cascadia rupture to a specific night within minutes. The precision is remarkable. The implication is cold. 326 years have passed. The Nankai Trough tells a parallel story. This subduction zone runs approximately 900 kilometers along the southeastern coast of Japan, where the Philippine Sea Plate dives beneath the Eurasian Plate at a convergence rate of approximately 6 to 7 centimeters per year. Historical records of major Nankai ruptures, the Hoei earthquake of 1707, the Ansei Tokai and Ansei Nankai earthquakes of 1854, the Showa Tonankai earthquake of 1944, and Showa Nankai earthquake of 1946, describe a fault that ruptures in segments, sometimes simultaneously, sometimes in closely spaced pairs, separated by hours or days. The Hoei event, which ruptured the entire length of the trough in a single catastrophic sequence, generated a tsunami that reached heights of over 20 meters along portions of the Japanese coast and killed an estimated 5,000 people at a time when coastal populations were a fraction of what they are today. The current interseismic gap, the time since the last major rupture, is now 80 years for the southern segments and over 300 years since a full margin event comparable to Hoei. The Japan Meteorological Agency and the Cabinet Office of Japan have assigned a probability of between 70 and 80% for a major Nankai Trough earthquake occurring within the next 30 years. That figure is not alarming in isolation. It is alarming when placed beside what deep-sea monitoring networks recorded in early 2026. The instruments that caught the anomaly are not dramatic-looking devices. The Dense Ocean Floor Network System for Earthquakes and Tsunamis, DONET, is a system of seafloor observatories deployed by the Japan Agency for Marine Earth Science and Technology, known as JAMSTEC. It consists of over 50 sensor nodes connected by fiber optic cables on the seafloor directly above the Nankai Trough seismogenic zone, recording ground motion, pressure, and temperature at depths of up to 4,000 meters. These nodes measure displacement in fractions of a millimeter. The data streams continuously, in real time, to shore-based facilities where automated detection algorithms flag anomalies for human review. What the algorithms flagged was a slow slip event, but not a routine one. Slow slip events, sometimes called silent earthquakes, are episodes of fault movement that release tectonic stress without generating significant seismic shaking. They occur on a timescale of days to weeks or even months, accumulating displacement equivalent to a moderate earthquake, but doing so gradually that the energy never concentrates into a destructive seismic wave. They were unknown to science until the late 1990s, when GPS networks became sensitive enough to detect centimeter-scale ground deformation occurring over weeks rather than seconds. The discovery fundamentally changed how seismologists understood the subduction zone stress cycle. The slow slip event detected above the Nankai Trough in early 2026 was anomalous in two specific ways that are generating intense scrutiny. First, its location. Previous slow slip events in this region have consistently occurred in the shallow outer portion of the subduction interface, the region where the fault transitions from locked to freely slipping as depth increases. This event showed displacement signals consistent with activation deeper in the fault zone in a region that geodetic models had classified as fully locked. A locked patch releasing strain through slow slip rather than accumulating it is not, by itself, catastrophic. But it signals a change in the mechanical state of the fault, a redistribution of stress that can, under specific conditions, trigger accelerated loading on adjacent locked patches. The second anomaly was the duration. Standard slow slip events in subduction zones typically last between 2 days and several weeks before the fault relocks and the cycle begins again. The event logged above the Nankai Trough continued for an unusually extended period, with geodetic signals showing ongoing displacement well beyond the typical window. Extended slow slip duration has been observed as a precursor pattern in at least one well-documented case. The 2011 Tohoku earthquake in Japan, magnitude 9.0, which was preceded by anomalous slow slip activity on the northern Japan trench interface in the months before rupture. That earthquake killed approximately 20,000 people. The tsunami it generated reached run-up heights of over 40 meters in some locations. The Cascadia story carries its own distinct urgency. The subduction zone stretches approximately 1,000 kilometers from northern California to southern British Columbia, where the Juan de Fuca plate dives beneath the North American plate at a convergence rate of roughly 3 to 4 centimeters per year. The locked zone, the portion of the fault interface where the two plates are fully coupled and stress is accumulating, extends from the seafloor at the deformation front to depths of approximately 25 to 30 kilometers. The width of this locked zone, combined with the convergence rate and the 300-plus years of accumulated strain since the 1700 rupture, produces a calculated moment deficit, the total stored elastic energy, equivalent to a magnitude 9.0 to 9.2 earthquake. The new data from the University of Washington, drawn from deep-sea sensor networks and GPS arrays across the Pacific Northwest, indicates that portions of the Cascadia locked zone have begun showing unexpected deformation signals. Not the familiar episodic tremor and slip that Cascadia researchers have documented since the early 2000s, rhythmic slow slip events that occur every 12 to 14 months in the transition zone between the locked and freely slipping parts of the fault. The new signals are coming from a different depth range. They are subtle. They are within the noise threshold for older instrumentation. The newer network, with its improved sensitivity baseline, resolves them clearly. The myth that deserves direct confrontation. Here is the one embedded in how earthquake risk is typically communicated to the public. The phrase overdue earthquake is used casually in news coverage to describe both Cascadia and Nankai, and it carries an implicit logic. If the recurrence interval is 300 years and 300 years have passed, the earthquake is overdue the way a library book is overdue. It will come eventually, and the longer you wait, the more likely it becomes. Tectonic faults do not work like library return dates. Recurrence intervals are statistical averages extracted from geological records that span multiple rupture cycles, typically 5 to 10 events at most, because the record does not extend further back with sufficient resolution. The variability around those averages is substantial. Cascadia paleoseismic data, compiled from turbidite sequences in offshore sediment cores and from marsh stratigraphy at coastal sites from Washington to Northern California, documents rupture intervals ranging from 150 years to over 1,000 years between events. What the 300-year figure actually represents is the mean of a distribution with significant spread. What makes the current situation scientifically significant is not that the clock has run out. It is that the physical state of the fault, as measured directly in real time by instruments that did not exist a decade ago, has changed in ways that are inconsistent with the models that assigned it its current hazard parameters. Models are built on assumptions. When the data contradicts the assumption, the model must be rebuilt. And in the process of rebuilding it, in the urgent recalculation of stress distributions and coupling coefficients and moment deficit estimates, a new picture is forming. one that the research community is still assembling, still debating, still refining. And it is not a reassuring picture. The specific mechanism by which a slow slip event in the deep locked zone could trigger a transition to fast, seismogenic rupture is not fully understood. This is not a gap in data. It is a gap in fundamental physics. The boundary between stable sliding and unstable, self-accelerating slip that produces a destructive earthquake involves rock mechanics operating under conditions of temperature, pressure, and poor fluid chemistry that cannot yet be fully replicated in any laboratory on Earth. What can be modeled is the stress transfer. When one patch of a fault releases strain, it loads the adjacent patches. If those adjacent patches are already near their failure threshold, already carrying stress close to the maximum that the rock can sustain before slipping, a small addition can be sufficient. The question of whether the adjacent patches on either Cascadia or Nankai are near that threshold is precisely what the current data cannot yet definitively answer. But it is the question every seismologist working on these systems is now trying to answer as fast as their instruments and their models allow. Rock does not bend. That single fact, so obvious it barely seems worth stating, is the foundation of everything that makes subduction zone earthquakes so extraordinarily violent and so different from almost any other geological process on Earth. When stress is applied to most materials gradually enough, they deform. Metal bends, clay flows. Even glass, over centuries, will sag under its own weight. But crystalline rock in the upper crust, granite, basalt, gabbro, responds to stress accumulation, not by deforming gradually but by storing it. Every year of tectonic convergence adds elastic strain energy to the locked fault interface the way winding a clock spring adds tension. The rock compresses, stretches microscopically, and holds. It holds for decades, for centuries. The energy does not dissipate. It waits. The technical term for this behavior is brittle deformation. In the uppermost 15 to 20 kilometers of the crust, where temperatures are below roughly 300 degrees Celsius and confining pressures are relatively modest, rock behaves as a brittle solid. It accumulates elastic strain up to a threshold, and then it fractures, not gradually, instantaneously. The rupture front propagates along the fault plane at velocities between 1 and 3 kilometers per second, which is close to the speed of seismic shear waves in crustal rock. The entire energy stored over hundreds of years releases in a window of seconds to minutes. The transition from locked to rupturing is governed by a framework called rate and state friction, developed primarily through the work of James Dieterich at the USGS and Andy Ruina at Cornell, through experimental and theoretical work conducted from the 1970s onward. The core insight of rate and state friction is that the frictional resistance of a fault surface is not a fixed number. It depends on two variables: the current sliding velocity and the contact history of the fault surface, how long the two sides have been in stationary contact, and how that contact has evolved at the microscopic level. A fault that has been locked for 300 years has developed what the framework calls a high-state variable. The asperities, the microscopic contact points between the two rock faces, have grown, interlocked, and strengthened through a process called contact aging or fault healing. The longer the fault is locked, the stronger those contacts become. This is counterintuitive. A stronger fault sounds safer. But a stronger fault requires more stress to initiate slip. And when slip finally initiates, the frictional resistance drops sharply as the contact points break and the sliding velocity increases. That drop in friction as velocity increases is called velocity weakening behavior, and it is the mechanical signature of unstable, self-accelerating slip. Once velocity weakening begins, the physics becomes self-sustaining. As the fault starts to slide, friction drops. As friction drops, the driving stress exceeds the resisting stress by a larger margin. The fault accelerates. The acceleration generates heat through frictional dissipation. Temperatures at the slip surface during a major earthquake have been estimated from pseudo-tachyllite, fossil fault glass formed by frictional melting, to reach between 900 and 1500 degrees Celsius locally. That heat further reduces friction. The process feeds itself until the available elastic strain energy is exhausted, which happens when the stress on the fault drops below the dynamic frictional resistance and the rupture decelerates and stops. For the Cascadia subduction zone, the geometry of this process adds a layer of complexity that makes it unlike any other subduction zone currently being studied. The Juan de Fuca plate is not a simple, uniform slab. It is young, the oldest portion being only about 10 million years old, and therefore relatively warm and buoyant compared to the ancient cold slabs driving subduction at Tohoku or at the Mariana Trench. A warm slab is less dense, and less dense material resists subduction. This means the driving force of Cascadia subduction is lower than at many comparable zones. The convergence rate of 3 to 4 centimeters per year is modest, but the locked zone is wide. The coupling extends across a fault area estimated at roughly 100,000 square kilometers, and the accumulation of moment deficit over 326 years has produced a stored energy budget that the geometry of the fault cannot release partially. When Cascadia ruptures, the physics strongly favor full margin rupture. The evidence for this comes from the Paleoseismic record. Offshore sediment cores collected along the Cascadia margin by teams from Oregon State University and the USGS contain 13 distinct turbidite layers, synchronous margin-wide deposits, that record 13 full or nearly full margin rupture events over the past 10,000 years. A turbidite is a density current deposit. When a major earthquake shakes the continental slope, sediment previously accumulated in submarine canyons avalanches downslope and spreads in a distinctive graded layer across the abyssal plain. The simultaneous occurrence of turbidite deposits in cores from multiple canyon systems, from Washington to Northern California, is the geological fingerprint of a single large rupture activating the entire margin at once. 13 events, 10,000 years. The math produces an average recurrence interval of approximately 750 years, but the actual intervals range from 200 years to over 1,000 years, underscoring the statistical spread discussed in the previous section. What the turbidite record cannot tell us is the stress state of the fault between events, and that is precisely what the current generation of monitoring instrumentation is attempting to measure directly. The Nankai Trough presents a different mechanical configuration, but the physics of failure are governed by the same rate and state framework. The Philippine Sea Plate subducts beneath southwestern Japan at a steeper angle than the Juan de Fuca Plate dives beneath North America, and the subducting plate carries a thick sediment blanket scraped from the seafloor, an accretionary prism that has been building for millions of years and now forms the Kii Peninsula and portions of the Shikoku coast. This sediment-rich interface changes the frictional properties of the fault. Water-saturated sediment under compression releases pore fluid, and pore fluid pressure is one of the most critical variables in fault mechanics. Elevated pore pressure reduces the effective normal stress on a fault, the component of stress pressing the two fault surfaces together. Normal stress is what makes friction work. Press two surfaces together harder and they resist sliding more strongly. Reduce the normal stress, and the same applied shear stress can exceed the frictional threshold and initiate slip. In subduction zones with thick sediment inputs, pore fluid migration through the fault zone creates spatially variable effective normal stress, producing patches of the fault that are mechanically weaker than their surroundings. These patches are called conditionally stable zones. They will not generate fast seismogenic slip on their own, but they can be triggered into unstable slip by a stress perturbation from adjacent locked patches. The DONET network data from early 2026 shows strain release signals originating from a depth range consistent with the conditionally stable zone at the up-dip edge of the Nankai locked patch, the shallow seaward portion of the fault where sediment is being actively accreted and where pore pressure gradients are steepest. A slow slip event in this location does not directly rupture the locked zone. What it does is redistribute stress. When the conditionally stable zone slips slowly, it transfers shear stress onto the adjacent fully locked patch deeper in the subduction zone, the patch that has been accumulating strain since 1946. The magnitude of that stress transfer depends on the geometry of the slip and the rigidity of the surrounding rock, and it can be calculated from the geodetic displacement field using elastic dislocation modeling. The calculation is not alarming in isolation. A few centimeters of slow slip on the shallow interface adds a small fraction of a bar, a unit of pressure, to the stress on the deep locked patch. the deep patch is already carrying hundreds of bars of accumulated stress. The addition from a single slow slip event is, by itself, insufficient to bring a healthy fault to failure. But the question that the current data is forcing onto the table is whether the deep locked patch is already at, or very close to, its failure threshold. Whether the stress it is carrying is not hundreds of bars below failure, but tens of bars, or fewer. That question cannot be answered from surface observations alone. The locked zone on the Nankai Trough is between 10 and 35 kilometers below the seafloor. No drill hole reaches it. No direct measurement samples the stress state of the fault rock at that depth and pressure. What can be done, and what research teams at Kyoto University, the Earthquake Research Institute at the University of Tokyo, and JAMSTEC are actively doing, is to construct forward stress models constrained by decades of GPS and INSAR surface deformation data, calibrated against the known slip history of previous events and extrapolated to the current date. Those models produce a range of estimates for the current stress level on the deep locked patch. The range is wide. The uncertainty is honest. And the lower bound of that range, the most optimistic scenario, the one that says the fault is furthest from failure, still places the Nankai deep locked zone within a stress regime that would be consistent with rupture within the coming decades. The upper bound is a different number entirely. Seismology has an instrument sensitivity problem that is only beginning to be resolved. The global seismographic network was optimized historically to detect earthquakes above a certain magnitude threshold and to discriminate nuclear weapons tests from tectonic events. The frequency bands and dynamic ranges of its sensors were not designed to resolve the subtle, slow, low-frequency deformation signals that turn out to be some of the most critical precursory information in subduction zone physics. The new generation of broadband ocean-bottom seismometers, deployed in increasing numbers along both the Cascadia margin and the Nankai Trough over the past decade, operates across a much wider frequency range, from the infrasound frequencies of slow-slip tremor to the high-frequency body waves of micro-earthquakes. The picture these instruments are assembling, data point by data point, sensor node by sensor node, is a picture of two fault systems that are not static. They are not simply locked and waiting. They are mechanically active at levels that older, coarser instrumentation could not resolve, trembling with low-frequency earthquakes, breathing with slow slip cycles, and responding to stress perturbations from distant large earthquakes in ways that suggest the coupling between segments of each fault is tighter, and the system closer to a critical state than the models built on surface observations alone had indicated. What a critical state means, in the language of fault mechanics, is a system poised near the threshold where a small perturbation can initiate a cascade, not guaranteed to cascade, not certain to rupture imminently, but operating in a regime where the margin between stability and failure has narrowed to the point where the question is no longer whether the physical conditions for rupture exist. The question is what form the trigger will take. In the spring of 2011, a seismograph array off the coast of Tohoku, Japan, recorded something that, in retrospect, the scientific community had the instruments to see but not yet the interpretive framework to understand. In the weeks before the March 11th magnitude 9.0 rupture, the fault interface beneath the Pacific Ocean was moving, not in the violent, high-frequency burst of a conventional earthquake. In a slow, deep, creeping signal, low-frequency tremor clustered in the transition zone between the locked and freely sliding portions of the subduction interface. The signal was in the data. It went unrecognized in real time. After the earthquake, after the tsunami, after 20,000 people were dead and the Fukushima Daiichi nuclear plant had entered meltdown, seismologists went back through the archived records. The precursory tremor was there, unmistakable in retrospect. A slow slip event had occurred on the shallow interface in the weeks prior. Microseismicity had clustered in patterns consistent with stress loading on the deep locked patch. The fault had been communicating its state in a language that the scientific community was only beginning to learn to read. That recognition, the retrospective identification of precursory signals in the Tohoku data, was the single most consequential development in subduction zone seismology of the past 20 years. Not because it proved that earthquakes are predictable, they are not in the deterministic sense that the word implies, but it demonstrated something more subtle and more important. that the fault system, in the months and weeks before a major rupture, enters a physically distinct state that leaves measurable traces in the observational record. The challenge is reading those traces in real time, with enough confidence to act on them, before the rupture, rather than after. The scientific response to Tohoku triggered a global reassessment of subduction zone monitoring infrastructure. Japan, already operating the most dense seismic monitoring network in the world, accelerated the deployment of DONET and its successor system, DONET-2, extending fiber optic seafloor observatory coverage along the full length of the Nankai Trough. The United States, recognizing that the Cascadia margin had no equivalent offshore monitoring capability, initiated the Ocean Observatories Initiative, a National Science Foundation program that deployed the cabled array, a network of seafloor instruments connected by over 900 kilometers of fiber optic cable on the Juan de Fuca tectonic plate, becoming fully operational by 2015. These were not incremental upgrades. They represented a categorical shift in the observational capacity of geoscience. The transition from a discipline that studied subduction zones primarily through their seismic outputs, after the fact, to one that could monitor the mechanical state of a fault interface continuously, in real time, from instruments positioned directly above the seismogenic zone. What the new instruments revealed across both margins was a world of fault behavior that the previous generation of land-based seismographs had been almost entirely blind to. Episodic tremor and slip, the rhythmic slow slip cycles that occur every 12 to 14 months on the Cascadia transition zone, had been discovered in 2003 by Gareth Rogers and Herb Dragert at the Geological Survey of Canada, using a newly upgraded GPS network in British Columbia. The discovery was immediately recognized as significant. Here was a fault-releasing strain, not through destructive earthquakes but through quiet, episodic creep, synchronized across hundreds of kilometers of the fault length, repeating on a clock-like schedule. The mechanism producing episodic tremor and slip remained debated for years. The tremor itself, a low-amplitude, long-duration seismic signal with no clear P-wave or S-wave onset, sounding on seismographs like sustained noise rather than a discrete earthquake, was traced to the slow rupture of small fault patches in the transition zone, each patch slipping for seconds to minutes and radiating low-frequency energy, with thousands of these microslips occurring in rapid succession to produce the emergent tremor signal. The GPS data showed that during each tremor episode, the surface of the Pacific Northwest moved eastward, in the direction opposite to the long-term westward creep associated with plate convergence, by a few millimeters, indicating that the fault below was slipping in the subduction direction and releasing a fraction of the accumulated interseismic strain. The critical insight that emerged from a decade of Cascadia tremor research was geometric. The episodic tremor and slip zone sits immediately downdip, deeper, from the locked zone. The two zones share a boundary. When the transition zone slips during a tremor episode, it transfers stress onto the base of the locked zone above it. The transfer is small, fractions of a bar per episode, but cumulative over decades of repeated tremor cycles. The locked zone is not isolated from the stress dynamics happening immediately below it. It is coupled to them. The 2025 and 2026 observational record for Cascadia shows a tremor pattern that departs from the established 12 to 14-month periodicity in a specific way. The inter-episode intervals have shortened, and the spatial extent of individual tremor episodes has expanded northward along the margin. A compression of the episodic tremor and slip recurrence interval has been documented in at least one prior case as a precursory pattern. In the months before a magnitude 6.8 earthquake on the southern Cascadia margin in 2001, tremor activity in the region intensified before the event. The 2025 to 2026 pattern is not identical to that precedent. The scale is different, the location is different, and a single analogy does not constitute a forecast. But the pattern is being tracked by every research group working on Cascadia with an urgency that the previous decade of monitoring did not generate. The Nankai revelation came from a different direction entirely, from the drilling ship Chikyu, operated by Jamstek as part of the International Ocean Discovery Program. Chikyu is the most capable scientific drilling vessel ever built, designed specifically to penetrate the Nankai Trough accretionary prism and reach the seismogenic fault zone at depth. Between 2007 and 2022, successive drilling expeditions recovered core samples and deployed borehole instruments, temperature sensors, pore pressure gauges, seismometers, at progressively greater depths within the fault zone. The deepest borehole, site C002, penetrated to approximately 3,058 meters below the seafloor, entering the hanging wall of the Megasplay Fault, a secondary fault branching from the main décollement that some models identify as a potential tsunami generator in its own right. The borehole instruments at site C002 recorded something unexpected in 2023, a pore pressure transient, a sudden localized increase in fluid pressure within the fault zone that was not associated with any surface seismic event detectable by land-based or ocean bottom networks. The pressure pulse propagated upward through the borehole over a period of several days before dissipating. Its source, constrained by the pressure waveform and timing, was consistent with a small slip event on the deeper décollement, a patch of the main fault interface slipping aseismically at a depth of approximately 5 to 6 kilometers below the seafloor, releasing pore fluid that had been trapped under elevated pressure by the compaction of subducted sediment. Pore fluid release from a slipping fault patch is not, in itself, alarming. It is a normal part of the subduction factory. Water-bound in clay minerals and sediment pores is progressively expelled as the material is buried and compressed, and some of that fluid migrates into the fault zone where it influences the frictional properties of the interface. What made the 2023 pressure transient scientifically significant was its timing relative to the slow slip event simultaneously detected by the Donnet surface pressure sensors. The two signals, a slow slip event on the shallow interface detected by seafloor pressure gauges, and a pore pressure transient in a deep borehole consistent with slip on the deeper interface, occurred within the same 2-week window. The implication, if the spatial and temporal correlation is causal rather than coincidental, is that the Nankai fault system was experiencing simultaneous slow slip at two different depth levels on the subduction interface. The shallow slow slip in the conditionally stable zone at the up-dip edge of the locked patch, and a deeper signal within or immediately below the locked zone itself. A locked zone that shows internal deformation signals is, by definition, no longer fully locked. The language in the published literature describing this observation is carefully qualified. The authors note that the correlation could reflect a common fluid source rather than mechanically coupled slip events. They note that the borehole instrument record is short. Site C002 has been continuously recording for only a few years, and that a single anomalous event cannot be distinguished from the background variability of a complex fault system without a longer baseline. They recommend continued monitoring and additional drilling to install instruments at greater depth. The recommendations are sound, the caveats are scientifically appropriate, and the data remains what it is. The first direct instrumental evidence from inside the fault zone of mechanical activity in the Nankai locked zone during the current interseismic period. No previous generation of seismologists had that evidence. Not because the fault was not doing this before, but because no instrument had ever been there to record it. The implications extend beyond Japan and the Pacific Northwest. The Hikurangi subduction zone off the east coast of New Zealand's North Island has been instrumented with a similar combination of seafloor observatories and scientific boreholes under the International Hikurangi Ocean Bottom Investigation of Tremor and Slow Slip Program, HOBITS. Hikurangi produces the shallowest well-documented slow slip events of any subduction zone on Earth, with some episodes occurring at depths of only 2 to 5 kilometers, close enough to the surface that they generate measurable seafloor uplift detectable by pressure sensors and GPS buoys. The Hikurangi data has become a natural laboratory for slow slip physics because the shallow depth makes the events more accessible to instrumentation. What Hikurangi has demonstrated is that slow slip events in the shallow locked zone are not anomalies. They are a normal part of the subduction cycle at some margins. The question is not whether shallow slow slip occurs on Cascadia or Nankai. The question, the one that connects the Hikurangi physics to the current anomalous signals on both target fault systems, is what happens when slow slip events begin occurring in portions of the fault that had previously shown no such behavior, when the spatial footprint of slow deformation expands into the fully locked zone. That expansion, on two of the most hazardous subduction zones on the planet, simultaneously, is the event that the current scientific community is attempting to characterize, quantify, and understand before the fault characterizes it for them. At 11:46 in the morning on March 11, 2011, the seafloor off the Tohoku coast of Japan moved. Not metaphorically, not gradually. A fault patch measuring approximately 500 kilometers in length and 200 kilometers in width, an area larger than the state of California, ruptured in a single, continuous, self-sustaining cascade that lasted approximately 160 seconds. 160 seconds, the duration of a television commercial break, the time it takes to boil water. In that window, the accumulated elastic strain of centuries released instantaneously, and the ocean floor in some areas displaced horizontally by as much as 50 meters, a distance longer than half a football field, in under 3 minutes. The seismic waves radiated outward through the crust at kilometers per second. At the surface, ground accelerations in the near field reached values that exceeded the design tolerances of structures that had been engineered specifically for major Tohoku earthquakes. The Japanese building codes, among the most stringent on Earth, had been calibrated to a maximum credible earthquake of magnitude 8.2 based on the historical record. The actual event was magnitude 9.0, and because the magnitude scale is logarithmic, that difference of 0.8 units represents not a modest overrun, but a release of energy approximately 11 times greater than the design maximum. The tsunami arrived at the coast 11 to 30 minutes after the rupture, depending on location. The first wave was not the largest. The coastal topography, bays, headlands, river mouths, channeled and amplified the incoming energy differently at every point along the coastline. In Miyako Bay, run-up heights reached 40.5 meters above sea level. The inundation in Miyagi and Fukushima prefectures reached inland distances of up to 10 kilometers across flat coastal plains. Pre-event hazard assessments had estimated maximum inundation of 1 to 2 kilometers in those same areas. The gap between the model and the reality was not the result of negligence. It was the result of a fundamental underestimation of what the fault was physically capable of, specifically of a phenomenon that the Tohoku rupture revealed for the first time at full scale: shallow megathrust slip. Standard rupture models had assumed that the shallowest portion of the subduction interface, the region closest to the seafloor, where sediment is soft and the fault transitions from locked to freely sliding, would not participate in a major rupture. The reasoning was mechanically sound. That shallow zone has low normal stress, high pore pressure, and velocity-strengthening frictional properties that should inhibit the self-sustaining slip acceleration required for seismogenic rupture. The models treated it as a passive region that would simply be dragged along by deeper rupture propagating upward, contributing little displacement and therefore little tsunami generation. The Tohoku fault disagreed entirely. The shallow interface slipped by up to 80 meters in some areas, the largest fault displacement ever instrumentally recorded in a subduction zone earthquake. The extreme shallow slip was the primary driver of the tsunami's catastrophic height. Because the seafloor displacement was concentrated near the trench, in shallow water, the initial wave was taller and carried more energy than any rupture model calibrated to historical events had predicted. The Miyagi and Fukushima prefectures had built seawalls designed for the historical maximum. The 2011 tsunami overtopped them by margins that, in some locations, exceeded 15 meters. The direct implications for Cascadia and Nankai are not academic. Both fault systems have thick sediment accumulations at the shallow interface, the accretionary prism that has been building for millions of years and that blankets the uppermost locked zone in water-saturated compressible material. Pre-Tohoku models of both systems similarly assumed that this shallow zone would contribute minimal slip in a major rupture. Post-Tohoku dynamic rupture models developed specifically to incorporate the revised understanding of shallow interface mechanics produced substantially different results. Three-dimensional fully dynamic rupture simulations for the Cascadia subduction zone, published in the Journal of Geophysical Research in 2021, demonstrate that shallow slip of 20 to 30 meters is physically consistent with the stress conditions and frictional properties of the Cascadia interface. Those simulations produce tsunami wave heights at the Pacific Northwest coast, ranging from 15 to 30 meters, depending on rupture geometry and the extent of shallow interface participation. The simulations are not predictions. They are physically plausible scenarios, constrained by real data that define the upper envelope of what a Cascadia megathrust rupture could produce. Portland, Oregon sits approximately 160 kilometers from the Cascadia deformation front, protected from the open ocean, but threaded by the Columbia River, which flows directly from the coast to the city. A major Cascadia tsunami would not reach Portland. The seismic shaking would. Ground motion models for a magnitude 9 Cascadia rupture, calibrated against Tohoku and against the amplification characteristics of the Willamette Valley sediment basin, produce peak ground accelerations at Portland comparable to those experienced in the most severely shaken areas of Tohoku. The duration of strong shaking is estimated at 3 to 5 minutes. Seattle sits on a sediment-filled basin, the Puget Lowland, that amplifies seismic waves through a resonance effect. The soft sediment responds to incoming seismic energy at its natural frequency, dramatically increasing ground motion duration and amplitude relative to bedrock sites. The same effect contributed to the severe building damage in Mexico City during the 1985 Michoacan earthquake, where the ancient lakebed sediments of the Valley of Mexico amplified ground motion from a magnitude 8.1 event occurring 350 kilometers away and collapsed hundreds of reinforced concrete buildings. Seattle's basin geometry is different from Mexico City's, but the physics is identical. Across the Pacific, the Nankai scenario carries a different but equally quantified dimension of consequence. The Tokai region of Japan, the stretch of coastline between the Izu Peninsula and the Kii Peninsula that sits directly above the most heavily loaded segment of the Nankai locked zone, contains the highest concentration of critical infrastructure in Japan. The Shinkansen bullet train network's central artery runs directly through this region. The Tomei Expressway, the primary road corridor between Tokyo and Osaka, runs parallel to the coastline throughout the expected inundation zone. The Hamaoka nuclear power plant sits on the Shizuoka coast, within the projected tsunami inundation area for a full margin Nankai rupture. It was shut down by government order in 2011 following Tohoku and has remained offline pending the construction of a tsunami barrier, a seawall 18 meters high that was completed in 2017. 18 meters. The Tohoku tsunami reached 40 meters in Miyako Bay. The Japanese government's Cabinet Office published its revised Nankai Trough Megaquake Damage Assessment in 2012, incorporating the lessons of Tohoku and the revised shallow slip models. The assessment estimated up to 320,000 fatalities in a worst-case scenario involving simultaneous rupture of the entire trough, the Hoei type event, combined with nighttime timing, winter conditions, and failures of tsunami warning compliance. Economic damage was estimated at 220 trillion yen, roughly equivalent to 1.4 trillion US dollars at current exchange rates. Approximately one-third of Japan's annual gross domestic product, concentrated in a window of minutes. The human geography compounds the physical hazard in ways that pure seismology cannot capture. Approximately 1 million people live in designated tsunami inundation zones along the Nankai Trough coastline. The prefectures of Kochi, Tokushima, Mie, and Shizuoka have invested heavily in vertical evacuation infrastructure. Concrete tsunami refugees built on elevated platforms above the inundation line, accessible within the warning window. The warning window for near-field tsunami, the time between rupture and first wave arrival, in some coastal towns along the Kii Peninsula, is estimated at 2 to 3 minutes. 2 to 3 minutes. The rupture itself lasts longer than the warning window. The post-Tohoku decade produced one of the most intensive reassessments of tsunami hazard methodology in the history of geoscience. The concept of a level 2 tsunami, an event beyond the historical record, physically plausible but previously excluded from design standards because its low probability made it economically impractical to defend against, was formally incorporated into Japanese coastal engineering standards in 2013. The distinction between protecting life and protecting property was made explicit in national policy. Seawalls are designed for the Level 1 event, the historically documented maximum. Vertical evacuation is the strategy for the Level 2 event that overtops them. That policy acknowledges something that previous generations of hazard management had avoided stating directly. There is a level of rupture that no engineered barrier will stop. When a fault the size of Cascadia or the full Nankai Trough releases its stored energy simultaneously, the physical scale of the event exceeds the capacity of infrastructure to absorb it. The correct response to that physical reality is not paralysis. It is the rapid, practiced, disciplined movement of human bodies to high ground, before the ground stops shaking, before the water withdraws from the shore in the characteristic drawback that has confused and killed coastal populations throughout history, before the first wave arrives. The ground is going to move. The water is going to follow. The only variable that science, engineering, and policy can meaningfully change is how many people are standing in its path when it does. And right now, on two fault systems that have just shown anomalous mechanical behavior for the first time in the instrumental record. The scientists whose instruments detected that anomaly are not asking whether a rupture will occur. They are updating the probability estimates that determine how urgently the answer to the second question must be acted upon. The seismographs are running, the borehole instruments are recording. The GPS networks are logging millimeter-scale ground motion every 30 seconds across thousands of stations. The data is accumulating. The fault is not waiting. There is a word in Japanese, jishuku, that translates roughly as voluntary self-restraint, a social contraction in response to collective grief or threat. After the 2011 Tohoku earthquake, the word circulated through Japanese society in a different register. Not as restraint from celebration or excess, but as a kind of enforced reckoning with what the ground beneath the Japanese archipelago actually is and has always been. Not a stable platform. A thin, tectonically violent crust stretched across one of the most geologically active convergence zones on the planet, where four tectonic plates meet in a configuration that has produced some of the most powerful earthquakes in the instrumental record. Japan did not choose its geology. Neither did the Pacific Northwest of North America, nor the coasts of Chile, nor the islands of Sumatra, nor any of the other communities that live above the subduction zones threading the margins of the Pacific Ocean. The Ring of Fire, as it has been called for over a century, a name that captures the volcanism but understates the seismicity. The Pacific Ring of Fire accounts for approximately 90% of the world's earthquakes and 81% of the world's largest earthquakes. It is not a metaphor. It is a physical boundary. The perimeter of the Pacific Plate and its neighboring microplates, grinding against the surrounding continental and oceanic plates in a process that has operated continuously for hundreds of millions of years and will continue long after any civilization currently living on its margins has ceased to exist. The specific geological configuration that produces subduction zone megathrust earthquakes is not a rare anomaly in Earth's history. It is the dominant mode by which the planet manages the thermal energy escaping from its interior. The mantle convection cells that drive plate motion are ultimately powered by the residual heat of planetary accretion, the energy deposited 4.5 billion years ago when the proto-Earth was assembled from the collision and merger of planetesimals in the early solar system, supplemented by the heat generated by the radioactive decay of uranium, thorium, and potassium in the mantle and crust. The planet is a heat engine. Plate tectonics is the mechanism by which it releases that energy. Earthquakes and volcanoes are the exhaust. That framing is not intended to diminish the human consequence of what a Cascadia or Nankai rupture would mean. It is intended to locate that consequence within the correct physical context. The Earth is not doing something unusual. The Earth is doing what it has always done. What is unusual is that in the current geological moment, several billion human beings have built their cities, their infrastructure, their food systems, and their communication networks on the moving surface of a planet that they have, for most of human history, been able to treat as static. The Cascadia subduction zone was not identified as a major seismic hazard until 1987. Before that year, the scientific consensus held that the Pacific Northwest was tectonically quiescent, that the Juan de Fuca plate was subducting aseismically without generating significant earthquakes, because the geological record showed no historical major events in the period covered by written records. The absence of evidence was mistaken for evidence of absence. The discovery came from a geologist named Brian Atwater, working for the USGS, who was examining coastal marshes in Washington state. In the stratigraphy of those marshes, he found evidence of sudden catastrophic land subsidence. Layers of soil and vegetation abruptly buried under tsunami sand deposits, with ghost forests of drowned trees rising from the tidal flats, their root systems still in place, their trunks bleached and preserved. The ghost forests were the geological memory of a coastline that had dropped suddenly by 1 to 2 meters as the locked fault beneath it ruptured and the elastic strain energy was released. The land, which had been bowed upward by the locked subducting plate, snapped back downward. The trees, whose root systems were calibrated to a land surface that no longer existed, drowned in the new tidal inundation. Radiocarbon dating of the drowned tree roots placed the last major Cascadia subsidence event in the late 17th century. The Japanese orphan tsunami record confirmed the date as January 26, 1700. The Pacific Northwest had been living above a seismic gap, a section of the subduction interface accumulating strain with no historical rupture in the written record, for over 3 centuries, and nobody had known. That ignorance has now been corrected. The paleoseismic record is established. The monitoring infrastructure is deployed. The physics of the rupture process is understood at a level of mechanistic detail that was not available to Atwater's generation or to the generation before it. The probabilistic hazard assessments are updated continuously as new data arrives. The building codes in Seattle, Portland, and Vancouver have been revised, though the gap between revised code and the existing built environment remains enormous, because most of the infrastructure in those cities was constructed before 1987. Oregon has the highest proportion of unreinforced masonry buildings of any state on the West Coast. Unreinforced masonry, brick construction without steel reinforcement, is one of the most dangerous structural typologies in earthquake engineering. It fails suddenly, without warning, shedding heavy masonry onto the occupants below. The Armenian earthquake of 1988, magnitude 6.8, killed approximately 25,000 people, primarily because of the catastrophic collapse of unreinforced masonry and poorly constructed Soviet-era concrete panel buildings. A magnitude 9 Cascadia earthquake would shake the Pacific Northwest at intensities far exceeding those of the Armenian event for 3 to 5 times longer. Oregon's Seismic Rehabilitation Incentive Program has been working to identify and retrofit the most critical unreinforced masonry structures: schools, fire stations, hospitals, but the pace of retrofitting has been limited by funding. As of the most recent inventory assessments, thousands of unreinforced masonry buildings remain standing in Portland, Salem, and other Willamette Valley cities. They are not invisible hazards. They are on maps. Their addresses are known. The structural assessments have been completed. The gap is not knowledge. The gap is political, will translate it into infrastructure investment at the speed that the hazard demands. The same gap exists in different forms along every subduction zone coastline on Earth. In Japan, the gap takes the form of the tension between the Level 1 and Level 2 tsunami design philosophy, between what can be defended against with seawalls and what requires evacuation. The 19 trillion yen invested in coastal protection infrastructure after Tohoku is the largest engineering investment in tsunami defense in human history. Seawalls averaging 12 meters in height now line over 400 kilometers of the Tohoku coastline. They are an extraordinary engineering achievement, and the most recent dynamic rupture simulations for a full margin Nankai Trough event produce tsunami heights that exceed them. The seawalls buy time. They attenuate the first wave. They reduce inundation extent for the moderate scenario. For the extreme scenario, the one that the physical record says has happened before and the stress models say is accumulating toward, they are a partial measure. The Japanese government knows this. The coastal communities know it. The vertical evacuation towers are the acknowledgement, architecturally encoded in concrete, that the extreme scenario is real and that the defense against it is, ultimately, movement. Geoscience in the early 21st century occupies a position of extraordinary and uncomfortable clarity. The tools exist to monitor fault systems at a resolution previous generations could not have conceived. The physics is understood well enough to define the envelope of plausible outcomes with quantitative precision. The paleoseismic record extends the observational baseline back 10,000 years. The probabilistic hazard models are updated continuously. And the conclusion that all of this monitoring, all of this physics, all of this history converges upon is not ambiguous. Both the Cascadia subduction zone and the Nankai Trough will produce magnitude 9 class earthquakes in the future. The recurrence intervals are not perfectly regular, but they are bounded. There is no physical mechanism by which the stress accumulation can continue indefinitely without rupture. The moment deficit on both faults is now large enough that even the most conservative stress models produce a major rupture as a certain eventual outcome, differing only in timing. And the anomalous mechanical signals detected in 2025 and 2026, the expanded slow slip footprint on the Cascadia transition zone, the deep pore pressure transient in the Nankai borehole, the recalculated coupling coefficients on both margins have updated the timing estimate in a direction that the community is not comfortable describing as reassuring. What separates this moment from every previous moment in the history of these fault systems is not the geological situation. The faults have been loading since 1700 and since 1946. What is different is the observational capacity, the network of seafloor instruments, borehole sensors, broadband seismometers, and GPS arrays that have, for the first time, placed human eyes directly on the fault interface during the interseismic period. What those eyes are seeing is a fault system that is mechanically active, spatially complex, and operating closer to a critical state than the previous generation of models indicated. Science cannot specify the date. The physics of nucleation, the process by which a slow, stable slip event transitions into a fast, unstable rupture, involves spatial and temporal scales that current instrumentation cannot fully resolve, and rock mechanics at conditions that no laboratory on Earth can yet reproduce with perfect fidelity. The uncertainty is real, and it is honest. What is not uncertain is the accumulated moment deficit. What is not uncertain is the shallow slip physics that Tohoku revealed. What is not uncertain is the inundation potential mapped by the dynamic rupture models. What is not uncertain is the 326 years of elastic strain stored in the Cascadia locked zone and the 80 years stored in the Nankai deep patch, compressing, stretching, waiting, in the manner of all brittle rock, for the threshold that converts that stored potential into kinetic reality. Brian Atwater found the ghost forests in the tidal marshes of Washington state and read in their drowned roots the memory of a coastline that had not survived the last rupture intact. Those trees did not know they were growing on a locked fault. The marshes did not know they sat above a seismogenic zone that would one day, without warning, drop them into the sea. The difference between those trees and the cities that now stand on the same ground is not geological. It is informational. The cities know. The scientists know. The hazard maps exist. The physics has been written down and peer-reviewed and published and translated into building codes and emergency management frameworks and vertical evacuation tower designs. The Earth has been recording its own history for 4.5 billion years in the language of rock strata, turbidite layers, slick-inside surfaces, and ghost forests. It has been patient in the way that only geology can be patient, indifferent to whether the record is read, indifferent to whether the conclusions are acted upon, indifferent to the timescale of human planning horizons and budget cycles and electoral terms. The fault will move when the physics requires it to move. The only question that has ever been within human power to answer is whether we will have moved first.